I've said it before, and I'll say it again. Reactions that form carbon-carbon bonds are such an important part of organic chemistry that they are almost always named after someone. And there is one particular reaction that proves so popular with undergraduate organic chemistry students that once they learn it, they try to use it everywhere. Good afternoon. Today we are discussing the Grignard reaction. For today's video, we're going to define the Grignard reaction as any reaction that involves a Grignard reagent. So now the question becomes, what is a Grignard reagent? These reagents have the general formula RMgX, where the R refers to an organic group, the Mg is the element magnesium, and the X refers to a halide, most commonly bromine. And although this is how we normally represent it, it is actually very common for these reagents, once they are in solution, to coordinate to the solvent molecules, giving a tetrahedral shape around the magnesium metal center. And these reagents are actually pretty easy to synthesize. You take something like an alkyl bromide or other alkyl halide and mix it with magnesium in dry ether under an inert atmosphere. And these dry inert conditions are important because Grignard reagents can react with both oxygen and water. When a Grignard reagent does react, it does so as if it were a carbon ion, with the carbon atom directly connected to the magnesium acting as our nucleophile. And one of the simplest reactions we can do is to take a Grignard reagent and pour it over some dry ice. Dry ice is the common name for solid carbon dioxide, and when our Grignard is added to it, that nucleophilic carbon atom attacks that central carbon of the CO2. And in doing so, we generate the conjugate base of a carboxylic acid. All that's left is to acidify the solution and then isolate our product. For example, the conversion of 2-bromobutane into 2-methylbutanoic acid. And if this was all Grignards did, it would still be a very useful reagent, but they can do oh so much more. Grignard reagents can react with almost any molecule that contains a carbon-oxygen double bond, as long as there are no acidic protons present. Because if we were to try and react our Grignard with a carboxylic acid, it would be rapidly protonated and destroyed. But this rapid reaction with protons actually can provide a means by which to deuterate a specific position in an organic molecule. So instead of using a carboxylic acid, we could use either an ester or an acyl halide, sometimes also called acid halides. These react with two equivalents of our Grignard reagent to give a tertiary alcohol. And there is another way to use Grignard reagents to generate a tertiary alcohol, and that is to react them with ketones. In this example, we use bromobenzene to form our Grignard reagent, which is then mixed with benzophenone in anhydrous ether, after which the reaction solution is acidified, giving triphenylmethanol as the final product. Now, if we wanted to generate a secondary alcohol instead of a tertiary, then we could use an aldehyde, and our final molecule would have one half coming from the aldehyde and the other half coming from the Grignard reagent. For example, we could react methyl magnesium bromide with benzaldehyde to produce 1-phenylethanol. Now, there is one aldehyde that doesn't react to produce a secondary alcohol, and that's formaldehyde. Because there are no additional carbons attached to our carbon-oxygen double bond, this will only react to form primary alcohols. In almost every example I have given so far, we could have switched which molecule was our Grignard reagent and which one was the source of our carbon-oxygen double bond. For example, instead of using methyl magnesium bromide and benzaldehyde to form one phenylethanol, we could instead have used acetaldehyde and phenylmagnesium bromide. And I think it is this flexibility that draws students to the Grignard reaction when they are performing retrosynthetic analysis. Hashtag topic for a future video. And we're not done yet. Grignards can also react with epoxides, opening the ring, and they attack from the less hindered side, making this a stereospecific reaction. And you might be looking at the product of this reaction and asking yourself, Grignard reagents have a lot of flexibility. Couldn't we have started with acetone? And the answer is yes, absolutely. Or we could have started with an ester or acyl chloride and reacted that with 2 equivalents of methyl magnesium bromide. All of these different synthetic routes would give us the same final product. So far in this video, we have mainly focused on reactions that give an alcohol as the final product. But Grignard reagents can do so much more. If we are very careful with our reaction conditions, we could generate aldehydes or ketones. Or we could move away from oxygen entirely and react with sulfur compounds to form thiols and thiol esters. Or you could take your Grignard reagent and turn it into a different organometallic reagent. But those are all stories for another day. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a topic you'd like to see covered in a future video, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.